Okay, so welcome back. May we continue on the session on the problems in shearing stress. So we are in the fifth problem. In the figure shown, we have here a plate connected by the rivet 20 millimeter in diameter. So we have unallowable stresses for bearing in the plate. We have 120 megapascal and 60 megapascal for the shearing of the rivet. So determine the minimum thickness of each plate and the largest average tensile stress in the plate. So on the earlier discussions, we have discussed that for this setup, there are three types of stresses. Number one, it is tensile stress on the plate. And then we have shearing stress in the rivet. So this is actually an example of shearing stress in the rivet or the single shear. So along this section, it will cut the section of the rivet. And then the bearing stress on the plate and the rivet, because there is a contact now between the rivet and the plate. So those are the shearing stress that we would like to apply here in this particular problem. So letter A, the minimum thickness of each plate, we will derive that out of the conditions of bearing stress and allowables for the shearing of the rivet. So shearing stress of the rivet is equal to shear force all over the shear area. So we multiply that again. So therefore, we have this expression. We have V is equal to tau times A. So this one, tau times A. However, this is P. But P here is also equal to the shearing, right? Because repeatedly, if we have a cutting force here, this is caused by P and to be resisted by the shear force V. So basically, this is a parallel axis. They are oppositely directed, therefore P is equal to V also. We can also say that this is equivalent to V. Okay, so P here is a shearing for the rivet, and the same P here is also the bearing force. Why is it? Why is that? Because if this is the rivet, we have a contact between the plate and the rivet. Okay, we have a contact between the plate and the rivet. See, this is the plate. This is the contact area. Okay, so this shaded portion here is the contact area. So this is resisting or the bearing force, PB. Or in short, P is also equal to the bearing force. Okay, on the single rivet. So this is a single rivet. If we have a series of rivets, say, for example, if we have a series of rivets, say, there are 3 rivets here, 1, 2, and 3. So basically, this is our P. What will happen is the bearing force will just be equivalent to or will be shared by the 3 rivets. So PB or P all over 3. Okay, so each of the rivet has P all over 3 and P all over 3 bearing force for each of the rivets. So just to cite that one. Okay, going back to this problem, anyway, we have a single rivet here, so therefore it is just only shared by one rivet. But if we have more than one, then P will just be divided into the number of rivets. Okay, so that's the principle of the bearing force. So applying now the bearing formula, bearing stress formula, we have sigma bearing is equal to bearing force all over bearing area. Okay, again we cross multiply that, we have this equation. Okay, so for the force, it was already derived out of this, although this is named as B, that is also the P, as I have been explaining repeatedly. Okay, so we just substitute that one, and then substitute the allowable bearing stress, and then the bearing area, that is diameter times thickness, because the contact between the plate and the rivet is again diameter times thickness. Okay, so that is the contact between. So out of this, therefore we can now derive directly the requirement of the thickness, satisfying both the shearing and the bearing stress. Okay, so letter B question, what is the largest average tensile stress in the plate? So as we can see, the average or the largest average can be found in a section with a reduction in the cross section. At this cross section class, say this is section, can we name this as section AA. At section AA, we have a section that is reduced. Why reduced? Because we have a hole here, so therefore if we are going to pull this plate, remember that the stress in the plate is a tensile force, or stretching the plate actually. Okay, so there is already a reduction in the cross-sectional area. Let me shade that one. So at this section, so this is actually the normal or the area of the simple stress or the normal stress. Sigma is equal to P over A. When we say largest average tensile stress, if we investigate this formula, if the area is reduced, what will happen to our stress? If the area is reduced, then the stress will be increased. Why? Because your divisor is decreased. When your divisor is decreased, then the value or the quotient or the result is a larger value. But if the area is larger, of course, it will reduce the stress. So on the section wherein there is no hole yet, say for example at any section, say this is section BB. So at section BB, we do not have any hole here, so therefore the area is not yet reduced. So meaning the value of the sigma there is smaller. When we have now a reduced area caused by this hole, it will tend to increase our sigma here. That is why we are considering a section that is reduced already in order to determine the largest average tensile stress. But if the question in the problem only requires tensile stress in the plate, then we can consider a section that is not yet reduced. But since we are addressing largest, then the largest is a section of the area that is already reduced caused by the hole. So that's it. So simply use this formula again. Cross multiply. P is equal to sigma times A. This one. And then substitute. We have already derived this one a while ago. 6,000 pi is the P. And then is equal to the sigma, or the largest average tensile stress. What is the area? Then the area here, take note, is a rectangular area. We'll just have to subtract the hole here, or the hollow space here. So as we can notice here that the total width of this is 110. It was reduced in a way that 20 is deducted on the gross length of this. So the net length, this is what we call the net length, because the hole here is already deducted. So the net length is 110 minus 20. We multiplied that by the thickness. Okay, the thickness was derived a while ago. It will become the area of the largest average tensile stress in the plate. So finally, this is the result, or the largest average tensile stress in the plate. So this is for problem number 5. So I hope this helps. Okay, so